Actually, good morning, I guess I could say. I was going to say good afternoon. I don't know why. RFNoC. If I were Steve Ballmer, I'd go around the stage saying, RFNoC developers, RFNoC developers, RFNoC developers. I'm very excited to talk about RFNoC every time that I do. And I hope I won't run over because just simply because I like talking about RFNoC so much. Yeah, we have a couple of updates. Matt asked on the sponsor talk if who had not heard about RFNoC, and 0 hands came up, and I was blown away by that. It made me really happy. It also made me realize I need to change my presentation a little bit because I did have some introductory material in there. Actually, who would like to have a very brief baseline introduction to RFNoC? Because it'll take time away from other slides, right? It sounds like there's some interest, but I'll try and keep it very brief. Okay, so RFNoC. Yeah, so I'll keep this very short. Also, actually, the architectural slides I'll keep very short. I want to talk a little bit more about how you get into RFNoC development and our roadmap, but also I want to keep a lot of time open for some demos. So as you can see, or maybe you cannot, I have a USRP X310 right here in front of me. It has the quiet fan, so it doesn't blow over the recording. And it has a UBX daughter board in there, and it's connected through a gigabit Ethernet to my laptop computer. So, if you have questions, you don't have to wait until the end, because if that's what you're interested in, then we might as well spend time on it. Okay, this is a slide I actually had up last year, and I only slightly updated it. And if this is your single takeaway from this presentation, then that's fine. So I think this is sort of a useful lie to explain RFNoC. RFNoC is for FPGAs what GNU Radio is for GPPs, and you'll find a lot of similarities between the two. I don't want to go through the full list and read them all out, but sort of the basic idea is both in GNU Radio and RFNoC, you are given a framework that lets you focus on whatever your DSP problem, for example, is. So GNU Radio will allocate all the buffers and make sure that data gets from one block to the other. And so does RFNoC, only on FPGAs. Here's a couple of sort of true statements about RFNoC. And once again, I'm not going to read them all out, but there's two I want to sort of emphasize right here. So first of all, and this is very important, I want to make this very clear, RFNoC is the architecture that we will be using for all of our USRPs going forward. There will be no, we won't be sort of iterating architectures every time. That there'll be like one single architecture, and it's RFNoC. So no more custom hooks to insert your FPGA code into USRPs as was in the past. All RFNoC. And the X310 and the E310 will have RFNoC going forward, and everything coming after that will as well. And the other one is, the other statement that I want to emphasize is, you can use RFNoC with GNU Radio. It works very well together, and I highly recommend using GNU Radio when going into RFNoC development, but it's by no means required. And actually, there's very little requirements on how to use RFNoC. You can just write raw C++. It also folds into other frameworks. But we tried very hard not to sort of add additional dependencies. So the dependencies for RFNoC are basically the same as for general UHD, which is pretty low. Okay, so yeah, a lot of good reasons to use RFNoC. Either because you have a big FPGA and there's lots of space and you want to make use of the processing, or because you have a very weak CPU, so you actually have to offload stuff off there. You don't want to run everything in software. And this is sort of this is sort of my favorite example. I've had this on most RFNoC slides since the very beginning. Classical application that makes a lot of sense. This could be something that a DSP 101 student is putting together after learning about spectral analysis. So we get data from somewhere, we calculate FFTs with Windows, magnitude square average. We call that Welsh spectral algorithm, spectral estimation algorithm. Then we plot that. This all makes sense from a mathematical point of view, except this won't actually run very well. So if you take like an X310, for example, run it at 200 megasamples, the only way you can actually get data off your computer is through 10 gigabit Ethernet or PCIe. 1 gigabit Ethernet won't do that, so most laptops, computers won't actually let you do that. Then you have insane number of samples coming in every second. You have to calculate FFTs on those. And FFTs and moving averages are just so obviously algorithms that are much better suited to run on an FPGA. So if we could just move all of those blocks on the FPGA, that would be nice. But we can't just insert them into the usurp. I think I have a, yes, I have a slide on that. Because then we lose all the modularity and the composability. Like we must never lose the ability to randomly connect blocks, or we're moving away from a generic SDR framework again. Anyone can just drop stuff on an FPGA, but what we need is something where we can arbitrarily connect signal processing elements like FFTs together, and that's what we try to do with RFNoC. Also, little limitations on what tools you can use, that's what I said earlier, and also very important, you don't want to spend time on anything that is not your actual DSP algorithm. So both GNU Radio and RFNoC try and do that, and obviously there's always going to be a non-zero overhead, but we tried hard to keep it small. The main, sort of the biggest restriction that we currently have is you have to sort of ahead of time make a conscious decision which blocks you want to have on a single FPGA, because there is limited space. So this could be an example of blocks that I throw onto my FPGA, and then I can connect them up in any way that I feel like it. So for example, here I would have one FFT and one FIR filter, and maybe even a soft core where I can run arbitrary software. But if I want a second FFT, then I have to make that decision ahead of time. So that's sort of, I would say, the biggest restriction right now. So I don't want to talk a lot about this. I have a lot of slides, though, and that is on purpose, so you can download them later. You can ask me questions, obviously. And by the way, you can ask me questions about RFNoC, of course, but there are a lot of other people, basically everyone from EDIS, that you can ask about RFNoC. There's a couple of people I do want to point out because they are new. So Suganda joined our team recently. She's sitting right here, and she's also working on the FPGA side. And Paul, maybe you can wave quickly, is also getting involved. And of course, Jonathan is sort of the main architect on the FPGA side, but you probably already know him if you've heard about RFNoC. Okay, so I'm going to skip straight ahead to this slide. And this is sort of trying to show you what happens when you move that FFT from that original example that I showed from your software onto the FPGA. First thing to notice, the actual flow graph doesn't look any different. It looks a little bit different. We have this green arrow, and the FFT is now called an RFNoC FFT. But just looking at it conceptually, you will immediately understand what's happening. Okay, we have samples coming from a radio going through an FFT, and then we do the mag square and the logarithm, and then we can plot it. What is very nice about this is under the hood, all these things are happening that you do not have to care about. So the green arrow means this is an RFNoC connection. So instead of connecting blocks in the regular way, GNU Radio will simply defer that instruction to connect something to UHD, and everything else is abstracted away. And then on the FPGA, we'll have a data flow that looks a little bit like this. The radio is now configured to send all its data to the FFT, and the FFT is configured to send all the data back to the host. And from there, it goes back into the regular flow graph. And I'm going to skip over some more slides. This is the other one I wanted to highlight. So if we zoom down a little bit into the bottom layer, this is what's going on. We have the radio, which is connected to the ADCs in this case, and it can control gains and stuff like that. It can also control when to start and stop streaming, when to receive, when to transmit. Then samples coming from the radio will be packetized, and this is also something to keep in mind. It's very, very important. In RFNoC, all data connections are packetized. And that's nice because we can now send packets to the next block, but we can also send them over the network because it's very easy to turn our RFNoC packet into a UDP packet. We just add another header. So the FFT would then unframe the samples and then pipe them through an AXI-Stream compatible IP block. And in this case, we would use the Xilinx FFT because it's already part of Vivado. We just get it for free. But what's nice is you don't really have to worry about too many things in this because everything that's called depacketize, a packetizer FIFO is already taken care of by the framework. So basically, you just drop down your IP, and you can focus on writing that IP. And that's what I really like about RFNoC. You might already have that IP. You might have written it for some other framework. Just drop it down and see how it works. And then you have to add a couple of files, but it won't take a lot of time on top of what you already developed. So here I'm going to slow down a little bit because this is sort of the news section. If you want to become an RFNoC developer, there is obviously a learning curve. This is similar to GNU Radio, but similar to GNU Radio, we have also tried to provide enough examples, or at the very least some tools to make it easier to get started. What do you need to do? Number one, you download UHD and the FPGA code. Now, currently, RFNoC lives on a feature branch called RFNoC-Devil, which you will have to check out. And once you build that, you will have all the RFNoC features available. Little hint, if you use PyBombs, it'll do that for you, even if you're doing it for the E310 and you need some embedded support. Now, I mentioned earlier that GNU Radio is highly recommended for testing and trying out RFNoC. So you will probably also want to install GNU Radio and GREdis. And we have a knowledge base article on the Edis knowledge base to get you started and give you some pointers where to start writing code, and also RFNoC module, which our intern Nicholas wrote, and I think which was also demonstrated on the Monday tutorial. So I'm actually going to pull up that page real quick just to give you an idea where it lives and what it looks like. So this is it. There we go. So this is our knowledge base in case you hadn't seen it yet. And there we go. This is the getting started with RFNoC development. We have probably forgotten something on this knowledge base. It hasn't been up for that long. And if you find it useful, but you find something is lacking, please let us know. We will happily update it. OK, let's go back to my slides real quick. And so you go through these steps, and then you can start developing RFNoC. And this is a picture I was very happy to already see on some other slides that were not by us. The most important part of that is clearly the FPGA IP. You can use any of these methods to develop it. And this is where the picture actually sort of doesn't properly show the relation of time, because you will be spending most time down here. Once you sort of have something, which is your RFNoC module, and you're fairly confident that it'll work, you can write some descriptors and controller code on top of that so it can be properly addressed from software. In most cases, that is as easy as writing 1 or 2 XML files. 2 XML files if you want to have a GNU Radio integration, and you need at least 1 for the UHD integration. And this XML file is basically a descriptor. It'll tell UHD what the block does to a very to the level that UHD needs to know it. For example, it'll say, OK, this block has 2 inputs and 1 output, and it has the following settings. That's the kind of description you put in here. So let's say you've gotten that far. This is sort of a more detailed description of the typical workflow it takes to develop any RFNoC block. Starting at the top, first of all, you create your custom AXI-based IP. And actually, it doesn't have to be AXI-based IP, because we also provide adapters, for example, for strobe-based IP. And also, you might already have that from a different project. So make sure it's all tested. You have test benches that pass. And then you have to think about how you want to expose this in RFNoC land. And there's 2 things you have to consider. One, what are the data IOs? And the second one is, which kind of settings does this block take? So, and I actually have an example for all of this, so I'm going to talk about that in a sec. Next, you need to make sure that this IP fits nicely into an RFNoC block. So the RFNoC block consists of modules that provide access to the rest of the RFNoC ecosystem. It'll take care of a lot of the data routing and all of that for you. And in many cases, you will have to write a little shim layer to connect your own block into RFNoC. You can test the entire RFNoC block from test benches. We have a lot of macros for that. And once you're confident that's working, you write those XML files that I mentioned earlier. And maybe you have to write some C++ code if it's more complex. I'll talk about that in a minute as well. And that's it. You're done. You can just drop down your RFNoC block in your flow graph and use it. And just to give you a little bit more of an insight what that actually looks like. So say we're developing an FFT core, we start at the top and we realize, oh, we don't actually have to write that because it already came with Vivado. So we drop down an IP core and it already comes with test benches. So let's trust Xilinx that it works. Then we think about how we want to expose the FFT to the user, and we'll say, okay, it'll have one input and one output, complex samples, and it'll accept packets that are of size FFT length, whatever that is. And then we have a couple of settings which we then expose through registers, which are the FFT size, output format is, do we want to output the complex values or maybe the magnitude square, FFT shift, and I kind of forgot the FFT direction, so is it an IFFT or a regular FFT? And there we go. So we write all those down, and this is what we'll later put into our host side control code. So we take that FFT and then we wrap it into some little layer that'll connect it to our what we call the NoC shell, which is our RFNoC infrastructure. We add some couple of test benches. So a very easy test for an FFT block is to put in a sine wave and then make sure that the correct bin is active and the others are all 0. And we have a lot of macros to make this kind of testing very, very simple. And we have all of these obviously available in our source repository. So you can just take a look at them and use them as examples. Couple of things to keep in mind when you're developing. Everything is access stream. I said that before. So if it's not access stream, then you have to go through some hoops to make it access stream, but we also provide examples for that. And there are many cases, like in GNU Radio, you have the sync block and the sync decimator, et cetera, et cetera. We try to sort of mirror that a little bit, and we have wrappers that will take care of decimation, interpolation, and streaming to bursty conversions for you. Also, we have an example of a source block, so it has no inputs, it only has outputs, and generates data. So that's sort of things to keep in mind when you're developing on the FPGA, and how do you, like, what can you use? As I said earlier, you can use all kinds of tools. We purposefully did not want to restrict RFNoC development to any single tool. So we have examples for Verilog VHDL, Vivado HLS, and anything that comes out of Xilinx. But really, there's no reason why any kind of netlist couldn't be loaded into an RFNoC block. So very little restrictions on our end, and the few that we have, we actually try and get rid of. So debugging, very important. Doesn't matter how good you are, you will eventually be debugging your RFNoC block, and we provide a lot of tools for that as well. I already mentioned the test bench macros, they come in very useful. You will have to do some debugging on the software, but the software comes with a lot of logging. You can just read the output and usually see what's going on. But something that's very, very useful is the GNU Radio integration, because you can just use everything that's in GNU Radio to visually inspect your code. And now I'm actually going to show you what that looks like, so to give you a better idea. So here's my GNU Radio companion, which I also installed through PyBombs. And here's an example that we had a while back as a tutorial. What I'm doing here is I'm generating a signal on the host computer, and I'm sending it to the FPGA and back. And on the FPGA, I'm going to calculate a moving average. So this is clearly a simple example for tutorial purposes. But what I'm going to do is I'm going to copy this functionality, which already existed in GNU Radio, and load it with the same parameters. I have two scopes connected, here and here. And just visually, I should be able to see the same signal coming out of here than it is here. So this is clearly not a a self-checking test bench, or well, in the software world we'd call it unit test. But while you're developing, this is extremely useful. And on a completely unrelated note, I love the fact that I can select these and go boom, and then have them all aligned. But that's just my OCD. Okay, I'm going to run this now, and as I said, it's really nice to know that you don't always have to use the radio, especially when you're developing and testing. So I can use my own synthetic signals and loop them back through my IP. Unfortunately, initializing an X310 takes quite a while. That's why I'm not showing off a lot more demos. which I'd love to. So while it's loading, or is it? Oh no, is it running on this screen? I was wondering where. There we go. So this is actually real-time data. So the bottom one is coming out of the RFNoC block, and the top one out of GNU Radio. And I can trigger here and then look at it more closely, but it's clearly very, very similar. If I would actually trigger and then zoom to the exact same window, you'd see it'd be the same. What I input, by the way, was a square wave, and then I made my moving average length the same as the half-duty cycle. That's why I get these triangles. So it's nice to see in GNU Radio and RFNoC we get the same results, so I'll consider that a success. By the way, this is the flow graph that I was mentioning earlier, where we do the Welsh spectral algorithm on the FFT. I'm just going to run this real quick. But one thing you'll notice when I run it, it doesn't look all that fantastic. So when we ran this for the first time, we were ecstatic because, wow, we can do 200 megasample, 200 megahertz wide processing on a laptop only with a 1 gigabit Ethernet connection. Fantastic, but fantastic, but we need to spice it up a little bit. So we found someone who could make it pretty, and that someone is Sylvain. He will actually be showing something very soon. I'm actually not going to steal his thunder though, so I'm going to stop showing off cool demos. I just need to get back to my slides real quick. And there we go. So one thing I did not talk about at all was what happens in software. Now we try to pull all the complexity as much as we could off the device, off the FPGA, and run that in software. So the software will take care of a lot of things such as flow control, making sure that data goes from the right spot to the next one, things like that. But most of it is sort of hidden away. So I didn't really want to emphasize it and steal time for demos during this presentation. Usually you do not have to do a lot of software development, except when you have very complex settings that need to be processed, and you need actual C++ code, for example, to calculate register values. Couple of logistics. So if you use PyBombs, then it'll help you set up your environment, even if it's on an E310, and you will currently need Vivado 2015.4. If you're working on the E310, you can use the Webpack version, so you don't have to buy that. Make sure that you don't try and do everything by hand through Vivado, because we provide a lot of make files, etc., to make it very, very easy for you. So last slide before we go into the cool stuff, and Sylvain, if you could start coming up to the stage at this point, thanks. It's a very, very coarse and some might say useless roadmap. I just wanted to give you a very high-level overview of what's going on. So if you're following the branch recently, then we had this huge merge of RFNoC Radio Redo, and this is sort of the result of, I don't know, like not quite a year, but many months of stabilizing and improving, which we all merged into RFNoC Devil. And when we released UHD 3.10, it already included RFNoC for certain use cases. So now we have GNU Radio Conference. At some point in the future, we will release UHD 4.0. At that point, there will be no more feature branch. There will be only UHD. It'll include everything. And all, as I said, all future devices will be running RFNoC. In the meantime, we'll be implementing all the features that are still missing or underdeveloped or not stable enough. Most importantly, the arbitrary connections where you can go radio to radio, device to device, stuff like that. A lot of stabilizing, making sure that we covered all use cases. And something that's also very important is we want to accelerate iteration cycles. We haven't fully mapped that out. Partial reconfiguration will probably play into that somehow. But currently, especially in the X310, it will take you up to 2 hours to just build the FPGA image. And that's not even including your development time. So it's slow, and we'd like to get that faster. So give it a try. If you go to the knowledge base, you'll find all the links that you need. And now I will hand over to Sylvain. Do we need to plug this in?
Yes.
Okay. So you've already seen Force for a million times. That, and what we did here was, where's my mouse cursor? Please, mouse cursor. What we did here was we took phosphor, well, silver into phosphor and put it onto the FPGA. So there's very little host code involved. I have to connect to the device first. Okay, so where do I go?
192.168.10.try24. Port it is 8080.
Oh. So 8080. So what I'm doing here, which you can't see because actually I want to pull this over before I do that. One sec. So I just went to a web address which is on this device. I will click start now. And I'll just hand off the mic and you can explain what's going on.
Thanks. So yeah, I'm sorry, my voice is. Okay, so this is basically the classic RFNoC phosphor flow graph running in the background. It's forwarding data through ZMQ to a web server that's running on the E312 here, and then sending those all the data, which the histogram data and the waterfall data, through WebSocket to an HTML5 page, and displays them on your browser using WebGL, basically. So the nice thing with this is, first you can actually open the page on several devices at the same time. You can stream that through the internet, depending on your upstream bandwidth, but it's not that much. It's in the like live video kind of bandwidth, 100 kilobyte per second, or things like that. I mean, I'm not a, where's the cursor here? Yeah. Currently there isn't many control except start, stop, and you can just slightly tune the FFT by just dragging it. If I can, oh, you need to click or something. Yeah, of course I tuned up the signal, but I mean, you get the idea. One thing that's nice as well is that on the E312, you can actually just plug a Wi-Fi dongle, start an access point, and then access that same web page through your mobile, basically. And so you can just have the E312 in your backpack and just walk around and monitor the spectrum. You have the same control, of course. It's kind of a little hard to show here, but you can drag the spectrum around the same way you do it. Obviously, it needs a lot more work to be a complete solution with more controls and stuff like that. But the aim is to make it a component that you can use in your own stuff. Yeah, that's it basically.
All right, let's thank our speakers. So we are completely out of time for questions, but I think Alex and Sergey, you guys want to come get set up? Okay, so why don't you guys come, if you guys can disconnect your hardware, if you guys want to come up and start setting up your demo, and while they're getting set up, we can take questions. Any questions from the audience? I see one in the back, Michael. Yeah, so if you...
Yeah, I know very little about FPGAs, but from the guys I see at work doing them, they're always fighting timing constraints. And I haven't seen any issue of those in the RFNoC presentation. So is that going to be an issue? Do you use high speed grade devices and clocking them low so it's more of a programming experience than a fighting timing constraint engineering experience?
So I would say we're fighting timing constraints as often as any other FPGA developer. It does happen, especially when the designs fill up the FPGA. There's sort of best practices you can do, and RFNoC I think actually helps a little bit in modularizing things, but especially when you're coming from like a software world and you're new to FPGA development, and you will start having you will have to read timing reports at some point, because what goes on in your IP is something that RFNoC does not care about. So if you have insane levels of combinatorial logic in there. This is unrelated to RFNoC. This is like putting, I don't know, too much I/O into software and then it'll run slower. It's the same kind of issue. We don't have a silver bullet solution for that, I'm afraid.
You talked about how long it's going to take, how long it takes to build an image for the E3 or the X310, I guess. What's the limitation there? Is it memory or cores, or is it both?
So Vivado doesn't actually multi-process all that much. So it stops, I think, at 4 cores. So I have a pretty beefy desktop machine, and when the thing is full, I'll still be synthesizing for maybe 2 hours on the X310. That's, you know, including place and route and all of that. On the E310, it's much faster. I think. Didn't you do that during the tutorial? No? Okay. Yeah, so 45 minutes. It also depends on the number of blocks you throw down. You can maybe speed that up. But as I said, we are working on making that faster.
How much feedback from RFNoC does a flow graph designer get when they instantiate something that's not really on the FPGA? So if I put 2 FFT RFNoC blocks in my flow graph and my FPGA didn't have 2.
Oh, okay. Yeah, you just get an error message saying that there's not enough FFT cores.
So it does logically look and see, am I?
Yeah.
Okay.
So when the session instantiates, it'll try and find a corresponding block on the FPGA for everything that you drop down. By the way, one thing that Nicholas is working on is that you take your GRC flow graph and then just basically throw that into the make system, and it'll just build the right FPGA image for you out of your GRC flow graph. It still will take 2 hours on the X310, but at least you don't have to figure out how to configure the make system or something like that.
So a topic that comes up on the mailing list quite often is the loopback feature, and as far as I know, it's not ready yet. So I was wondering what the difficulty is. Why is it so difficult to have that feature, and when it might be released?
Okay, I'm not going to give you a definite answer to the second question. It'll be released before the 4.0, and I'm pretty sure it'll be released before the end of the year. Why is it so hard? I don't want to go too much into detail, but I'll happily talk to you about it. I'll give you sort of a high-level answer, which is that we're doing all of this in public and working off of current UHD, which made a lot of assumptions about devices that are no longer true. So, for example, what happens if you do a loopback through your own block and then you have an overrun in the radio? Like, how would the host know? So we need a whole completely new sort of design for how to pass data between the host and the blocks if there's no actual data connection.
One more question.
So I know this is for a lot of the Edis boards that you guys are making. How easy would it be to port to my own custom hardware?
Well, depends on your own skills, I guess. I mean, all the code is up there. It's GPL code. Go take it, play around with it. That's the best answer I can give you right now.
Okay.
Okay, thanks everyone.
Thank our speaker. Thank you, Martin.